Hey folks, I actually did my hair today, so I thought I would keep the camera on and talk to you a little bit about chapter 3, which is about deep time. Deep time is a really important concept in historical geology. I think time is a funny thing because when we think about it in a human lifetime and then we compare it to the history of the earth, it's very hard to wrap your brain around. In a lot of ways, if you think about the expanse of a human lifetime, it's like you don't even exist in geologic time. You're so insignificant. But then in another perspective, like you're part of this incredibly long evolution and change of the Earth. So it's hard to think about scale. It's hard to think about the changes that we would see in a human lifespan and how that would be reflected in the geologic record. What humans will look like in the geologic record is something I think about every now and then. But in terms of how long we've been on the Earth, it is just really the last 2 million years that humans have been a force of the last 4.6 billion years. One time, a few years ago, I turned the hallway in MCC, in one of the hallways. It was about 175 feet long, and I turned it into a scaled model of the history of the Earth, and where one end of the hallway was where Earth first formed, and then the other end of the hallway, 175 feet later, was where we were today. And in that 175 feet, just the last 2 inches of that whole stretch were where humans were even around in the geologic record. So it's kind of crazy. It's a really cool concept that we'll kind of grapple with a couple times this semester. So when we talk about deep time, there's 3 big topics that your textbook talks about. And we're going to do them one at a time. We're going to start talking about the geologic timescale, which is in your, it's right on the left side of your course page because it's super important and you're going to come back to it several times this semester. And so one of the things you learned about in 101, to move on to the next topic, is absolute dating. And the age dating, where you use isotopes to get the age of things, which is really important in historical geology, especially when we look at events that occurred billions of years ago. What isotopes do we use for that, as opposed to things that have occurred since like the last ice age about 10,000 years ago? And then finally, we're going to talk about how the age of the Earth was first calculated. It's very fun. So this is a relatively simplified geologic time scale. And what you'll see is that it's divided into different periods of time. The largest time period, the largest expanse of time, is called an eon. And I'm going to be honest, when I went to school, these eons, especially down in the very earliest part of Earth history, were all collectively known as what's called the Precambrian. They were subdivided a little bit, and the numbers on this have changed in the last couple decades. I am old. But in general, the early history of the Earth is referred to as the Precambrian eon, and it has then been subdivided as geologic progress and knowledge has increased over time, and has been subdivided into the Hadean eon, the Archean eon, and the Proterozoic eon. And what's deceptive about this geologic timescale is that it looks like the Precambrian was just the very beginning. But in reality, the Precambrian eons, the Hadean, Archean, and Proterozoic, collectively account for 88% of the history of the Earth. And the reason that the most recent eon is so large in this geologic timescale is because we know so much more about the Phanerozoic eon. And you might remember from 101 when we did igneous rocks, we talked about phaneritic texture, and we talked about how that prefix phan meant visible. And so that's consistent here, because the suffix here, zoic, means life. So this means visible life. And that is because starting in the Phanerozoic, in the very earliest part of the Phanerozoic, which is a time called the Cambrian period, you really start to see really great evidence, indisputable evidence for life in the Phanerozoic eon. And to be honest, there's plenty of evidence for life in the Proterozoic, but at the time that this was really established, the Proterozoic eon People didn't know as much about like some of the trace fossils and the soft-bodied fossils that are associated with the Proterozoic eon. So really the Phanerozoic is when organisms started to make hard parts, which really increased their potential for being fossilized in the geologic record. So again, eons are the greatest expanses of time. Eons can be subdivided into what are called eras. And there are eras within all of the Precambrian eons, but for the purpose of this class, we will only talk about those when we get to those specific eons, and we're talking about them in some detail. We are going to talk about the eras of the Phanerozoic, however, because we know a great deal about. So the Phanerozoic begins with what's called the Paleozoic eon. So remember I said that zoic means life. So Paleozoic literally translates to ancient life. Then there's a huge mass extinction that occurs about 250 million years ago to end the Paleozoic era. And it ushers in the beginning of the Mesozoic era. Mesozoic means middle life. Meso means middle. So middle life. And that is really the age of reptiles on Earth. That also ends rather dramatically about 65 million years ago with another significant mass extinction. And it ushers in our current era, which is called the Cenozoic, which means modern life. And this is really the age of mammals. This is a time period when mammals became by far the dominant life force on Earth. We can see, though, that this isn't enough detail to really be able to describe some of the events that were occurring during these time periods. So eras are subdivided into shorter time periods called periods, ironically. And periods can extend for 100 million years or so. They're still relatively long. But all of these periods that we see, especially in the Phanerozoic, are marked by a significant geologic event. And we'll be talking about each of these eras in some detail, and especially when we talk about the Paleozoic, which is a relatively long era. You can see that this 200 million year time span, or rather almost 300 million year time span, is subdivided into several periods. And I'm going to draw your attention to this really quickly. So in the United States, we subdivide a time period called the Carboniferous period into the Mississippian and the Pennsylvanian period. The rest of the world collectively calls this the Carboniferous period. The reason we subdivide it in the United States is because the Mississippian period is defined by a time when pretty much most of the continental United States was covered in ocean water. And then in the Pennsylvanian, we have really extensive coal deposits that are formed that are economically significant. So we subdivide that in the United States, but most places in the world use the term Carboniferous period. As we look a little bit closer, periods can then be subdivided into what are called epochs. And there are epochs throughout all of the rest of the periods, but they're most significant when we're talking about Cenozoic geology. And that's because, especially in North America, there have been some very significant events that have occurred in the Pleistocene epoch. That is when that was the last ice age, really. There were 4 ice ages that occurred within the Pleistocene, and then once the Pleistocene epoch ended, we entered our modern epoch, which is called the Holocene. And it's also true that there's been a lot of debate about creating a new epoch called the Anthropocene. That prefix anthro should sound familiar to you because anthro means man, and that's because geologists have argued that we are now in the age of man because man has become such a dominant life form on Earth that we've really fundamentally changed the Earth. And some people argue that that is inappropriate, and then people have talked about where that division should go. So in the most updated geologic timescales, I don't believe that the Anthropocene exists yet. But the geologic timescale does change. There is an international group of people who get together every so often to go ahead and make these changes based on new scientific discoveries of the geologic time within the geologic timescale. This geologic timescale is kind of amazing. It was initially constructed by geologists really working around the globe. And it's kind of crazy to think about because initially geology kind of evolved as this hobby, really. People who were fossil collectors, people who thought rocks were cool, eventually started studying geology in a more scientific way. And they started being more rigorous around their field observations and about their fossil collecting techniques. And then they started using some of those relative dating techniques that we learned about in 101, like cross-cutting relations, original horizontality, superposition, things of that nature. And eventually they started organizing, and they'd get together and people would bring their field data and describe the rocks they were talking about. What they realized is that, well, so we all know, is that rocks aren't evident on the surface of the earth in many places, right? There's soil on top of them, there's vegetation on top of rocks. So what people would do is take really detailed notes of field sites of what are called outcrops. And that's what you're looking at here. This is an outcrop along the New Mexico-Colorado border. And I chose this picture for a reason. So what you see here is a series of what looks like limestone and shale. And you see that the limestone kind of naturally forms these bricks. It's pretty characteristic of limestone to weather into bricks and along joints. And then you see the soft shale. And so you see limestone, shale, limestone, shale, limestone, and so on and so forth. So it can be really confusing if you take detailed notes of an outcrop here at the New Mexico-Colorado border, and maybe you find another outcrop 15 miles away. It's hard to match up each one of these distinctive limestone beds because they all kind of look the same and they're all interspersed with shales. So there had to be some fossil evidence then that started to go with these beds to be able to start to correlate this limestone layer to maybe another limestone layer 10 miles away that was different from this limestone layer. It got really confusing. The other thing that happened is that every geologist who was initially describing their own outcrops also used their own words. They would name the outcrops and they would name the rock layers. So you might call this the Jared limestone, and then you might name this one the Anna shale, and so on and so forth. But your Anna limestone might have been someone else's Kevin limestone or something like that. And so what ends up happening is that the same rock layer ended up having different names based on where the geologists were describing them. So that's why communication was so important in early geology, because people really had to get together to figure out that they were which rock layer they were actually talking about. And then once they agreed, hey, your Anna limestone is my Kevin limestone, then they had to figure out, well, who described it first, because that's who gets to name it. It's very fun. So yeah, there were the same layers with multiple names. What ended up being really helpful was the adoption of absolute age dating. And the reason is because absolute age dating allowed us to say, and I'm totally messing these names up because I didn't write anything down, that this Jacob limestone, we found an ash bed in that, and that ash bed is 127 million years old. And then we also found an ash bed in the Anna shale, and that ash bed was 120 million years old. So then once we looked at our ash beds 15 miles away, we could say, all right, where's the 127 million year old ash? Where's the 120 million year old ash? And we could correlate that way. So absolute ages were absolutely important in the establishment of a good, robust geologic timescale. Okay. So let's talk a little bit more about age dating. Radioactivity was first discovered really not that long ago, especially if you think about the expanse of geologic time. So it was discovered in 1896 by a chemist named Henri Becquerel, who definitely looked like a French chemist. So Henri, I'm sorry if you can hear my dog snoring, he's very tired. Henri discovered the idea that there are radioactive isotopes that, again, isotopes are atoms that have an irregular number of neutrons in them. And those atoms or isotopes are called parent atoms. Many of them are unstable, meaning that the nuclear forces that need to hold these atoms together aren't strong enough to hold all of the particles, meaning protons and neutrons, in the nucleus of an atom. And so what they'll do is they'll undergo spontaneous decay and turn into fundamentally different atoms, which are called daughter atoms. So we're going to talk about the 3 ways that this can occur. And I'm going to be pulling up your geologic, or not your periodic table to illustrate how some of that happens. And then you'll get some time to practice with that. So there are 3 mechanisms of radioactive decay that we're going to discuss. The first one is the one that emits the highest number of particles and is actually most damaging to humans, and that's called alpha emission. And that's because what happens during alpha emission is that what's something called an alpha particle is ejected from the nucleus of a parent. So I made incredibly simple models here to illustrate what's going on during each one of these radioactive decay events. What happens during alpha emission is the ejection from the nucleus of a parent, the ejection of 2 protons and 2 neutrons, which is called an alpha particle. 2 protons and 2 neutrons in isotopic geology is, or geochemistry, which is a really cool field, is called an alpha particle. And it gets shot out of the nucleus of a parent, like that. So what that does, and this is how we end up with fundamentally a different atom. What that does is that it changes the atomic mass, first of all, of the parent. Each one of these particles weighs 1 atomic mass unit. So you can see that there's 4 particles ejected, so the mass of the parent drops by 4 atomic mass units. The other thing that happens is that the atomic number of the parent decreases. So I'm going to show you what that means here. I have a link to a periodic table. All right, so in this very dynamic periodic table, oh my God, I hope it doesn't ripple the whole time. What you see here above every atom is a number, and this is called the atomic number of the atom. So here's gallium, and the atomic number is 31. What that means is that this gallium has 31 protons in its nucleus. If I look at aluminum has 13 protons in its nucleus. If I look at selenium, it has 34 protons in its nucleus. So the atomic number is really the number of protons in a nucleus of an atom. So every atom in the universe that has 16 protons in its nucleus is sulfur. And what we saw is that during alpha emission, 2 protons are shot out of the nucleus. So if sulfur were to undergo alpha emission, it would lose 2 protons. It would then have 14 protons in its nucleus, and then it would be called silicon. So you can see that we start with 1 atom that has 16 protons. We drop the number of protons by 2 to 14, and the atom is actually now silicon. So conversely, we can do this all day, right? We can take molybdenum, which has 42 protons in its nucleus. And if we kick out 2 protons, 42 minus 2 is 40. If molybdenum underwent alpha emission, it would turn into zirconium because it had 40 protons then in its nucleus. Cool. All right, so that's one method of radioactive decay. A second one is called beta emission, and that's because a beta particle is emitted from the nucleus of the parent. So we know that inside a nucleus are protons and neutrons. What we don't often think about the fact is that neutrons, which we know are neutrally charged, they have no positive or negative charge, neutrons are actually composed of 2 particles that are merged together, which is really cool. Neutrons are composed of a proton and an electron. Remember that the mass of an electron is basically 0, especially for the level of detail that we're looking at here. So a neutron weighs 1 because a proton weighs 1 and an electron weighs basically nothing. So the neutron is composed of a proton and an electron, but what happens during beta emission is this is all within the within the nucleus of the atom is that a neutron will actually split within the nucleus of an atom, and it will turn into a proton and an electron. It will split into those two subatomic particles. And then the proton will stay within the nucleus, but the electron, which is called a beta particle, the electron is ejected from the nucleus of the parent, which is kind of crazy. So just to recap, within the nucleus, there is a neutron, and that neutron splits into a proton and an electron, and it kicks the electron out. So what that essentially does is, because an electron weighs nothing, this mass doesn't change at all. But we've now increased by 1 the number of protons in the nucleus. So during beta emission, we basically turn a neutron into a proton and kick out an electron. This is kind of crazy. So then if we look back at our periodic table and we pick another random element like potassium. Potassium has 19 protons in it, right? So if we were to take a neutron that's inside potassium and turn it into a proton, there would be 1 more proton in it. So that potassium would turn into calcium, which has 20 protons. Same thing as if we took phosphorus and we increased the number of protons by 1 in phosphorus, it would turn into sulfur. If we had oxygen and we ejected a beta particle and increased the number of protons by 1, it turns into fluorine. So you're going to get some practice with this once this little lecture video is over. All right. So the third type of mechanism for radioactive decay is called electron capture. And that's something a little bit different. So in electron capture, the parent is just floating around doing its parent thing, and it captures an electron. It sucks it into the nucleus. And there's electrons shooting around all the time, so it's not like there aren't random electrons that a parent can just capture. So an electron is captured by the nucleus of the parent, and then it's almost kind of like the opposite of beta particles, of beta emission here. So it's going to capture the electron, and then the electron that is captured will combine with a proton that is already inside the nucleus of the parent, and they will combine to form a neutron. So if we take a second here, we basically, in electron capture, take a proton and turn it into a neutron. So we haven't changed our mass because an electron doesn't weigh anything, but what we have done is we have decreased the atomic number, because when we take a proton and turn it into a neutron, there's 1 fewer protons because now it's a neutron, right? So if we go back to our periodic table, if we had nickel, which has 28 protons in its nucleus, and we absorb an electron and turn one of those 28 protons into a neutron, the number of protons then decreases to 27, and it becomes cobalt. Similarly, if we take antimony, which has 51 protons, and we drop the number of protons by 1 by turning it into a neutron, it turns into tin. All right, good stuff. I think that's enough complexity for now. I think we should practice that, and then we'll come back and we'll talk about how the age of the Earth was calculated. The last bit I wanted to talk to you about is that there are lots of different uses for isotopes. I know that in 101 we talked about them basically being used to determine the age of events, but there's other things that they can be used for. I'm just going to give you just a super general smattering of them. Here are a bunch of glacial erratics that were deposited as glaciers receded back to these mountains. You can use beryllium isotopes, and beryllium isotopes start to form as the rays of the sun first hit these erratics, and they can tell you the age of exposure on the surface of these erratics, so you can calculate the rate at which glaciers receded, which is cool. This is a map that illustrates what's called deep ocean circulation. So there are definitely wind-driven currents on the surface of the ocean, but ocean bodies of water will sink to the bottom of the oceans in two different places. One is here off the coast of Antarctica, and the second is off the coast of Iceland and Greenland here. And it begins very slow, deep ocean circulation, and it can come up. It will rise back up to the surface in a few spots in the Indian Ocean and then in the Pacific Ocean, which is what makes the part of what makes the Pacific Ocean water so very cold if you've ever been to the West Coast. But we can use what are called neodymium isotopes. Neodymium isotopes give us an idea of the oxygen content in the water, and so we can use it to as sort of ocean bodies of water will slink along the bottom of the ocean floor. They will accumulate more and more neodymium, mostly from the scales of fish. And we can use the amount of neodymium in sand samples along the seafloor to calculate how old that ocean water is, how long it's been. When I say old, how long it's been since that water was surface water. So we can use that to determine deep ocean circulation, both in the modern, and then we can collect really old ocean really old ocean samples to calculate past deep ocean circulation. So here are a series of layers of sand and clay, and they can be analyzed to calculate basically glacial advance and retreat. So each one, and we're going to learn more about this over the semester, but each advance and retreat of glaciers will create a layer of sand followed by a layer of clay. And we can figure out when those glacial lakes were present based on the carbon-14 date within those layers of clay. And that's because carbon-14 is used to date really geologically young events. You don't really, because carbon-14 has a relatively short half-life of about 5,000, almost 6,000 years, you can only really use it to date things that go back around 50 to at most 70,000 years of age. Okay. In some locations, groundwater flows very, very slowly in the subsurface due to lower permeability. In some cases, groundwater also takes a really long time before it is maybe used or drawn up by a well. So we can actually take samples along wells to find what's called bomb water. So during the 1940s and 1950s, when there was a lot of experimentation for nuclear testing, that nuclear testing created isotopes isotopes of hydrogen and helium, which created what's called bomb water. And we can, by finding bomb water, the water that we then find, we know was at the surface of it first percolated into the soil in the 1940s and 1950s, and we can use that to calculate the age of and the flow rate really of groundwater, which is kind of cool. So we use hydrogen isotopes to estimate the rate of groundwater flow. Okay. We can, and we will this semester, use oxygen isotopes as a way to estimate ancient paleo temperatures. So oxygen isotopes are evaporated at different rates, and they will condense into seawater at different rates. And we can use this by looking at layers of ice in ice core. This one is from Antarctica in what's called the Vostok ice core, and goes from today back 400,000 years. And we can use not only samples of gases from the ice at different time periods, but also the isotopes of oxygen in the ice to be able to figure out the paleo temperature, the actual temperature it was 200,000 years ago, for example. And it turns out in the last decade or so, there's been a lot of work with barium isotopes, because barium seems to behave very similarly to oxygen. So very cool. And finally, we can use the chemistry in people's teeth to infer ancient human migration patterns. So it turns out if you lived in an area where there's a high amount of, let's say, uranium in the soil, then your body would make bones and teeth that with a higher concentration of uranium in it. And we can use that to then figure out where people moved over time, because you take your teeth with you when you migrate, and we can say, this person has a really interesting signature. Maybe this person was first born in a location where there was a lot of tin in the soil. And we can go back and use geologic maps to figure out, well, where was tin common, and trace out actual migration of people. It's actually super, super cool.